Today, we're going to pull back the curtain on some of the invisible magic that's happening inside pretty much every microchip ever made. It's a process that's so fundamental to modern electronics, but you've probably never even heard of it. So, let's get right into it.
I mean, really think about it. We talk about processors and memory and all these fancy terms, but what are they actually made of? Well, it turns out one of the most critical components isn't a conductor at all. Nope, it's a perfect insulator, grown one single atomic layer at a time.
And that unsung hero is silicon dioxide, or SiO2. You might actually know it as quartz, or hey, even as the main ingredient in glass. But in the super tiny world of microelectronics, this simple little compound is literally the foundation of our entire digital lives. I'm not kidding. Without it, the device you're watching this on right now just plain wouldn't exist.
I mean, just look at this list. The sheer versatility of this material is what makes it so incredible. Think of it as the ultimate multi-tool for building chips. It acts like a perfect little stencil, right? Masking and blocking chemicals from getting to the super delicate silicon underneath. And maybe most important of all, it builds these tiny, perfect insulating walls that stop billions, literally billions of transistors from short-circuiting and messing with each other. Without that perfection, a chip would just be total chaos.
Okay, so if this stuff is so important, how on earth do manufacturers create a flawless, ultra-thin layer of it on a silicon wafer? Well, the main technique, the one that really makes all modern integrated circuits possible, is called thermal oxidation.
Let's break that down, because it sounds complicated, but it's pretty cool. You basically take a super pure silicon wafer, you stick it in an incredibly hot furnace, we're talking 900 to 1200 degrees Celsius, and you flood it with an oxygen-rich environment. It's kind of like a very, very controlled and precise form of rusting, where you're not getting ugly brown flakes, you're growing a perfect layer of glass right on the surface of the chip.
And you know, just like any good recipe, there are a couple of different variations, all depending on what you're trying to cook up. The two main methods are called dry and wet oxidation.
So first up is dry oxidation. And as the name suggests, this one uses pure oxygen gas. Now, this is the slow and steady method. It takes longer, but it creates an extremely high-quality, dense oxide layer with almost zero impurities. This is what you use for the most critical parts of a transistor, like the gate oxide that controls the flow of electricity. If that layer isn't absolutely perfect, the whole transistor is useless.
But what if you need to go faster? Well, that's where the second method, wet oxidation, comes in. Instead of pure oxygen, this one uses water vapor, basically super hot steam. This reaction is way, way faster. So this is the go-to when engineers need to grow a much thicker insulating layer, like for building those walls we talked about that isolate all the different devices on the chip. It's all about having the right tool for the right job.
All right, now we get to the really interesting part. Let's look at how this layer actually grows, because this is wild. It's not just like painting a layer on top of the silicon. No, something much more fundamental is happening to the wafer itself.
0.44. Just look at that number. That number is the key to one of the most mind-bending parts of this entire process.
Okay, so here's the deal. To create this brand new glassy layer, the process actually consumes the original silicon wafer. The silicon atoms right there on the surface, they bond with oxygen, and they literally become part of the new silicon dioxide layer. The chip is being built out of its own foundation.
This diagram shows what's happening perfectly. You see that dotted line there, the original silicon interface? That's where the surface of the silicon used to be. As that SiO2 layer grows, it expands outward, sure, but it also grows downward, eating into the silicon beneath it. So the new surface is actually higher than the old one was.
And this right here is the key takeaway. The boundary, the place where the pure silicon meets the silicon dioxide, it's not static. It's actively moving deeper and deeper into the silicon as the oxide layer gets thicker. This is a critical detail that engineers have to account for with like nanometer precision. It's incredible.
And that really brings us to the whole point of this unbelievably complex science: control. It's all about achieving absolute perfection and consistency on a scale that is almost impossible for us to imagine.
This quote just sums it all up, doesn't it? The entire business of making high-quality integrated circuits depends entirely on this one thing: being able to grow that perfect layer with the exact right thickness, the exact right properties, time after time, across millions and millions of chips without fail.
So, the next time you use your phone or your computer, just remember that invisible layer of perfectly grown glass humming away inside. It makes you wonder, right? What other invisible layers and unsung heroes of material science are hiding in plain sight, just making our modern world possible?